In the next subsection, I want to talk about the LCP array, the longest common prefix array. That will be an addition to the suffix array that allows us to solve many more of the problems that we could attack with the suffix tree, but now using just the suffix array. So what is the LCP array? To get you a little bit back awake and in shape, let's think about one of the applications, namely the length of the longest repeated substring. Remember, that was the single string version of the problem that Knuth conjectured would not be possible to solve in linear time. And it also was the first problem where we've seen that suffix trees can do this easily. Now, I'm asking you, what exactly was the feature of suffix trees that we used for this? I think all of these features that I listed here are actual features of suffix trees. So suffix trees can do all of these, and there's algorithms that make use of that. But specifically for this problem to find the longest repeated substring, there's really one of them that is very important for finding the longest repeated substring. Without that feature, you don't get anywhere close. The actual algorithm might implicitly rely on some of the others. So it's probably hard to say that any of these is completely irrelevant. But there's definitely one feature that I would say is the key feature for this problem. Okay, let's see what we have. I love to get the usual 25 people voting, so maybe we can spend another minute on this. But I do want to move on also to show you the construction algorithm of this. So maybe let's show the results here now. Also because most of the people got the most important thing right. So I marked the other answers as not correct, but the truth is that the algorithm probably uses some of the others as well. The traversal probably needs the constant time traversal to child or parent nodes. We don't really use the order of leaves, to be fair, to be honest. We don't really use the jumping to the leftmost leaf in the subtree. But the key thing is that we know the string depth of internal nodes, because remember, every internal node is something shared between at least two suffixes. Shared between at least two suffixes means it's a repeated substring, the path to that node, and the string depth is the length of that string on the path from the root to that node. So that is precisely what we need for finding repeated substrings, and then the maximal string depth of any internal node is the longest repeated substring. Right, so that was that. How can we possibly add this back to the suffix array? Internal nodes is inherently something in the tree structure of the suffix tree, and that is completely lost by simply looking at the order of leaves, right? I even said the order of leaves is exactly something in the suffix tree that we did not use for this problem. So how can we add this back? Remember, the algorithm for finding the longest repeated substring was like this. We compute the string depth of all nodes, and then we find one internal node with maximal string depth. So again, let's briefly do this here. String depth 1, 2, 3, 3, 1, 2. So the maximal ones are these two. And here you see there's two maximal repeated substrings in banana ban. It's ban, occurring ban, ban, here and there, and Anna, which occurs here and here in an overlapping way. But that's in general okay for repeated substrings. It seems unclear how to do this in a suffix array by itself, but if we add another piece of information, we can actually do it. And that is the LCP array, which is an array of numbers again. So that's similar to the suffix array, and that's similarly as before an advantage for implementing it. It doesn't have an entry for 0. That's just a technicality I want to point out. Usually I let all our arrays start at 0, as is convention in most programming languages. But for the LCP array, it's convenient not to do this. The rth entry in the LCP array is the length of the longest common prefix of two suffixes, namely two that are neighboring in the sorted order, or neighboring leaves in the suffix tree, namely those that start at position R and whatever is the next one. So the rth suffix in sorted array, in the sorted order, and the previous one. That explains why there's no entry for 0, because there's no previous entry for 0. So yeah, let me okay, we'll see the example on the next slide in full detail, so maybe that's enough. I just want to point out that between any two neighboring leaves, so these are, remember, left to right, the leaves, this gives you the suffix array. If you just walk around the tree in this manner, the suffix array of the string Anaban will be 9, 5, 7, 3, blah, 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 blah. That's what we used before. Now, between any two, we will have this LCP array. So the LCP array will correspond to the point between, it will always be something between two adjacent leaves. And if we take, for example, the 7 and the 3, this point corresponds to this node, the lowest common ancestor of these two leaves. And you'll see the LCP array stores essentially the string depth of this node. That's the connection to string depths and to finding longest repeated substrings. But we'll go over the example in full detail here. Let's make the full connection. Here's the suffix array, and it will be the same example. So remember, I promised it's 9, 5, 7, 3, 1, etc. 9, 5, 7, 3, 1, etc. So that matches up. That's the suffix array. These are the suffixes in sorted order. We can find the longest common prefix between those. So I wrote that in between. These overlap in terms of A. These have AN in common. These have ANA in common, etc. So these are exactly the labels of paths to internal nodes. That's no coincidence. Every internal node in a tree is the lowest common ancestor of two adjacent leaves. You can think about why that is true, but that's always the case in a compacted trie. So here we have again the suffixes in sorted order and their LCP values. These are the strings, and the LCP array stores the length of this shared prefix. Okay, that's all there is to it. Now, so far, this is just the definition. It's very elementary, very simple. You can sort all the suffixes, then you get the suffix array. You can compare how much do they overlap, then you get the LCP array. I've already hinted at a connection to suffix trees, but you can actually make this very explicit. And in a sense, these two arrays contain all the information about the suffix tree. And that's really cool, because that will mean those two together will allow us to compute the suffix tree. But we don't really have to do that. We can actually live with those two alone, but we'll come back to that. Let's see how this connection works. There's a notion of Lcp intervals. That is the range of the suffixes in sorted order that share a common prefix. And because they're sorted alphabetically, these are always intervals. So there's a trivial one with the empty string. Every string has the empty string as a prefix, so that's saying nothing. But we need a root for our tree, and the root corresponds to sharing at least nothing. Then there's a bunch of strings that start with an A, and these are all grouped together. These are these 4 strings. That's an LCP interval of 3 because the the shared prefix is always between these. So the length 3 here actually means 4 suffixes. Then there's a smaller interval of those that share AN. These are these 3, AN, AN, AN. And there's an even smaller one that share ANA. ANA, that's only these 2 suffixes then. Things can be degenerate, as in this case, there's only 2 that start with a B. The same 2 start with BA and actually BAN. So there's only this interval corresponding to this entire thing. And that will be an indication that there's an edge with a longer string label. So to make that connection complete, here's the suffix tree, again drawn sideways. And you can make a one-to-one connection between the internal nodes of the suffix tree and the LCP intervals. And these intervals are well nested, so whenever you have a smaller subinterval, it's completely contained in the parent interval. That's exactly as subtrees are contained in the subtree of the parent, etc. So this is a perfect mapping, and it means that all the information of the suffix tree is entirely contained in the suffix array and the LCP array. Okay? That's a really cool picture to keep in mind, because it means we can entirely, at least for implementing it, we can entirely do away with the suffix tree and only concentrate on these 2 arrays, which are much easier to store and to handle in code. But we effectively have the same information still present. Okay.